Hello, calculus scholars, and welcome to another episode of Fun Times with Calculus. Today we're going to be talking about one of my favorite subjects. We're going to be doing Lagrange multipliers. So, in all likelihood, you've never seen a Lagrange multiplier before. They're a really common solution tactic, but they're usually not covered in anything other than Calc 2. Now, there is a small chance that you maybe have seen them show up somewhere before, but in more likely than not, you haven't. So, what is a Lagrange multiplier? Well, basically, the idea is a Lagrange multiplier is going to allow you to add a constraint or a limiter, something that limits your possibilities, to an optimization problem. So when I say the word constraint or limitation, I want you to be thinking things like, oh, well, this month I only have about, $200 to invest in materials for whatever product I'm producing, that kind of thing. So you want to use that as a constraint. Everything I must spend must be under $200 for whatever I'm going to produce. Or maybe I can only, do 400 hours worth of labor this month because that's how many workers I happen to have and how much I'm willing to let them work. So it's a way to kind of like limit yourself according to what realistically is going to happen. And this is really common when you're trying to optimize something. So, speaking of, let's talk about what a constrained optimized problem looks like. So it's going to be when you have some function f of x, y, like we've seen so far, and you're going to have a constraint. On your x and y. So usually it's some form of equation. Like I said earlier, like maybe in total I make two products and I have only $200 I can spend on materials this month. So there's my limiter. Materials for product X, materials for product Y must add together and be equal to 200. Now we're using equal to, you could use less than or equal to, but we're going to assume you want to use as much of this as possible, so that you end up with, you know, using up all of your funds and producing as much as you can, and therefore probably making as much of the product as possible. So what we're going to do is we're going to have these two parts and we're going to combine them using Lagrange's method to figure out what is going to happen here. So let's talk about Lagrange's multiplier and how they look. So suppose you have a function to optimize. You guys know what optimize is? This means find a max or a min. So you're going to be using the d-test again today. We're going to call that z equals f of xy. So it's in terms of x and y. And a constraint g of xy equals 0. And it's very important that we've rearranged this to equal 0. So going back to our earlier example, what I would do is I would take this guy and I would subtract 200 from both sides to make it 0 on one side. And then for this one, g of xy would be x plus y minus 200. See how that's working? So I changed my constraint to be equal to have one side be 0 so that I can combine these two into what would be the Lagrange multiplier equation. So we'll make a new equation. Usually the symbol for this is either a capital F or a capital L for Lagrange, with a new constant called lambda equal to f minus, oh, yeah, I'm not going to be able to fit the x and y in here, so f minus lambda times our g function we made over here. Okay, so when you look at this, then to optimize this, lambda is just some value. That's why we use L for lambda. That will optimize your equation so that your L function, when you do its x derivative, you get 0. Your L function when you do its y derivative, you get 0. And then your L function when you do the lambda derivative, you get 0. I know this seems weird, but what this is going to allow you to do is essentially skip the d-test. So notice there's nothing I need to check. As long as I can find a value that does this, I've actually optimized it. Interesting, huh? Very different from what we've seen previously. I'm going to scroll up here. So let me write you out the steps for this so that you understand what's going to happen. So the first thing you're going to do is exactly what you saw me do, is we're going to rewrite your constraint so that one side is 0. Cool. Then step 2 is you're going to create the Lagrange function. I mentioned earlier, L of xy, and this new guy lambda is just going to be your f minus lambda g. And usually I'll simplify that a little bit to make the derivatives we're about to do a little bit easier. Step 3, hey, we're going to find the first 3 partial derivatives. So we're going to find derivative with respect to x, derivative with respect with y, derivative with respect with lambda. Started to write my lambda too early. Sorry about that. Step 4 is then we're going to look at and solve that system that we just found. So I'm calling it a system because we've got 3 equations set equal to 0. And it's going to take some work. There, I did it again. So excited to write that funky symbol that I keep, getting ahead of myself. And then step 5, of course, is going to be, to check your answer. Or and usually slash, and this is something important, actually write your answer in terms of x and y. So you're going to see me go through these steps in this next example. Hopefully you're ready for that. Let's move her on up. That is the wrong button, but it didn't register me touching it, so it didn't matter. Okay. If that went a little fast for you, remember you can always pause, rewind, and rewatch different parts of the video to help you out. Oh, shoot. I really wish this would go away. There we go. Okay, so we're going to maximize 3xy subject to the constraint that when I look at x plus triplet of y, I should be equal to 12. So there's my minimizer. So the first thing I'm going to do is rewrite the g of xy. And for me, that's going to be x plus 3y minus 12, because that'll make this side 0. So I'm just subtracting 12 over to the other side. Hopefully that's the easiest step for you. Now I'm going to make my Lagrange multiplier. I know that I'm pretty sure your book actually uses capital F for this, but I like L for Lagrange. So for this is going to be the f function, which is 3xy, minus lambda times x plus 3y minus 12, the g function. Now I'm going to take a second and just distribute that lambda and that negative to make this a little bit easier when I go to do my deriving. And usually I will write lambda in front of x, because although x is a variable, lambda is kind of treated as a constant, so like 3 lambda y minus 12 lambda. Oh, I didn't change all my signs. I need to fix that because it's a negative, right? So I got to be careful to distribute. So minus, minus, and then plus. Okay. I need to note to myself that writing with this pen is always larger than what I actually leave my space for writing it when we do it in class. Okay, now I need my 3 derivatives. So I'm going to do the x derivative first. So remember, when we're doing this, we're doing the partial with respect to x. We treat x as a variable and everybody else as constants, which means when I go to do the derivative of 3x times y, I'll derive the x and get a 1, so I'll just be left with a 3y. I'll derive the lambda x portion and get a minus lambda. And the rest of this doesn't have any x's in it, so those are all going to come out 0. Let's go to the y version. So same thing, I'm going to be treating y as my variable. Everything else is going to be treated like a constant. So x is a constant, y is my variable. When I derive the 3xy, I'm just going to get a 3x because the derivative of y is going to be a 1. The lambda x is going to be a 0 because there's no y's present. And then I'm going to get a minus 3 lambda from the 3y lambda part. And then 12 lambda is going to end up with, well, A whole lot of nothing because, 12 lambda. It doesn't have any y's. I'm sorry, that was longer than it needed to be. Now the lambda derivative. So be careful with your lambdas. Mine started to look like an x. Oops. So my first term, the 3xy, has no lambdas. That's going to be a 0. My next term is negative lambda x. When I derive the lambda, I'll just get a negative x. Negative 3 lambda y. When I derive the lambda, I'll give you a negative 3y, and then a plus 12. A good way to check yourself when you're looking at this is the lambda derivative should always just be the opposite of your constrained g, and that's a good check that you've done this correctly. Occasionally it will pick up other variable stuff as well, but that has to at least be there. Okay, so what we should do next is we should solve this system. So we're going to set everything equal to 0 and come up with something that is easy to solve. So now when I'm approaching this, I usually focus on the shorter or equations with less variables in them in general. So since these two, and in general the xy ones are the ones you're going to go with, both can be expressed in terms of lambda. I'm going to solve for lambda and then substitute them into each other. So for this first one, I can add lambda to the other side, and that'll give me 3y is lambda. And on the second one, I can add 3 lambda to the other side and divide by 3 and get that x is actually equal to lambda. So when I combine these two ideas, that tells me that 3y is actually equal to x because, well, they're both equal to lambda. And this is actually a move you'll use a lot. And you'll see me use a lot because it's a good strategy. If you can solve for lambda, you can usually set some sort of thing equal to each other and then use it in the other equation. So now that I got that 3y is equal to x, is that what I got? I feel like I messed something up here. Yeah, lambda, 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 lambda. Yeah. Oh, this is easy because then I've got 3y is equal to x. Well, I've got a 3y right here. Let's replace it with what it's equal to. It's equal to x. So I'm taking this and substituting it in here. So I'll have negative x minus x plus 12 equals 0. So I'll combine my two x's and subtract 12 over, and I'll get that negative 2x is negative 12. Lo and behold, that means that x is totally just 6. Now you can then take that back into here and say, ooh, I'll solve for y. So 3y is equal to 6, divide by 3, divide by 3. We'll get that y is 2, and I'm done. Now in this case, I didn't have to solve for lambda at all, and usually you can get around it that way. So this tells me that if I was doing this as a production function, oops, I would get 6 comma 2. And I didn't actually have to find lambda to do this, so kind of fun, maybe, depending on your definition of fun. I don't know. You guys know what I'm like at this point. Let's try another one, because, one example is never going to be enough, let's be honest. Sorry about that. Had to remind it that I have an ink pen. Let's take a look at this one. So if you're feeling pretty confident, I would encourage you at this stage to maybe pause the video, try number 2 by yourself, and then, come back and hit play and see if you got the same thing I did. Good times. Speaking of good times, I'm going to jump right to making my Lagrange function here. So I've got my original function, 4 minus x squared minus y squared, minus the new g function I would make would be a negative lambda times, we're going to end up with x plus 2y minus 10. Let's go ahead and do some distribution here. And we'll do our derivatives. Make your x's nice and distinct because you don't want them to look like your lambdas. If anything, make your lambda nice and curly so it's a little bit more understandable and looks like more of an upside down y. That's kind of fun. Okay, so first we're going with the second derivative. So really watch your signs with this one. There's a lot of negatives floating around. Derivative of 4 has no variables in it whatsoever, so that's going to disappear from every single one of these partial derivatives. We'll go ahead and do the derivative of negative 2x with respect to x, and that'll give me a negative 2x, and then a negative lambda, and there's nothing else with an x on it, so I'm good to go. Let's go to y. I'm going to get a negative 2y, and then a minus 2 lambda. Or sorry, not y, lambda. So I'm seeing 2 lambdas pop up here. We're going to do the same trick again. And then last but not leastly, x and y out. Anything with lambda on it's going to show up, so I'll get negative x, negative 2y, sorry I missed the 2, plus 10. Make sure it's clear that that's an x. There we go. Beautiful. All right. So set these all equal to 0. And then we're going to do some solving. So I'm going to focus on these two. I'm going to do the same trick I did before. I'm going to solve for lambda. So I'll get negative 2x is equal to lambda. And down here, I'm going to get that negative y is equal to lambda. So I'm doing that by adding lambda to one over to the other side and then dividing through by 2. If you can't do the algebra that fast, that's okay. You know, just go through it and take your time. And then since lambda is equal to lambda, that tells you that negative 2x is equal to y. Sorry, negative y. I'm going to drop the negatives on this and call it 2x is y because that'll make my life a little easier. So then I'm going to replace y with what it's equal to. So I'm going to go back over to my negative lambda function. So I have negative x minus 2 times y, but we just realized that y is 2x plus 10. But actually, I'm going to go ahead and subtract the 10 over because I know I'm going to have to do that eventually. Not 2y, 2x. Sorry about that. Okay, so let's distribute our 4. So I have negative x minus 4x equal to negative 10. We'll add our two x's together. Negative 5x equals negative 10. Hopefully you can divide by negative 5 and totally get that x is 2. Now that you know what x is equal to, we'll go back into here. And since y is equal to 2x and x is 2, we're going to get 4. So that tells us our solution is 2, 4, and there you go. Now, occasionally some of the ones in your assignment are going to ask you for the value of lambda. Remember, you have two ways of finding lambda up here. So now that you have x, you could just go plug it into here to figure out what lambda is, or you could use y. So clearly the lambda in this case is going to be negative 4. Good times, I hope. Should be fun. Let's do another one. Nope, I want to move it, not right a line. There we go. Whew, let's find the minimum value. What's kind of fun about this is there's no checking to see if it is a minimum. If you wanted to, you could do the d-test to this one. It's a little messy, but again, the Lagrange multipliers I think just adds a little bit more detail to finding the maxima and minima of this. Let's go ahead and set up our Lagrangian. Now you know a fancy word that makes you sound smart too, like, oh, what did you do? I learned the method of Lagrangian multipliers today, Mom. It was really cool. I mean, I don't know. Well, if you're not with your parents, maybe you could tell like your significant other, or I don't know. I'm assuming you're talking to people every day. And Lagrangian multipliers just sounds fancy, doesn't it? Lots of subtraction in this one too. Subtraction, action. Ooh. All right, let's do our derivatives. As I've said many a time before, at this point you should be like asking yourself, ooh, what's she going to do next? And hopefully you're getting the rhythm of this down. One of the nice things about this method is it always has the same steps. Set up my Lagrangian, do my partials, set them equal to 0, and solve. It's got a nice sort of flow to it. Let's do our derivatives. So with respect to x, I'll get a 4x here. I'll get nothing off that guy. Ooh, I'll get a negative y off of that. That's interesting. And then minus lambda. Ooh, this one's going to be a little difficult. I can tell because it's got some mixes of x's and y's. Different. Okay. What's up next? Oh, I got to do y. So here I'll get a 2y, a minus x. Make sure my x is distinct and not lambda-ish. Nothing, and a minus lambda. Interesting. This is going to get a little messy. Alrighty. Let's go ahead and do... Oh, no, wait. This isn't that bad. Don't worry about it. I make it sound scarier than it is. So for then lambda, I'll get a negative x, a negative y, and a plus 8. We're setting these all equal to 0 to solve. So as you've seen me do a million times before, I'm just going to add my lambdas to the other side to get what lambda is equal to. So for me, that's first equation, it's going to be 4x minus y. For the second equation, that's going to be that lambda, not x. Make it thicker, because then it's clear that that's a slashy poo. 2y minus x. So since these are both equal to lambda, that means they're equal to each other. See, I told you this was going to be too bad. Look at that. Not nearly as bad as it seemed before. Okay, so I'm just going to collect my x's to one side and my y's to the other. So I'm going to add y, because I like positivity, and add x to both sides. Those are both going to go away. Those are both going to go away. I'm going to get that 5x is equal to 3y. And this is another one that typically shows up. So I get this ratio, and I've got some choices to make here. I'm going to probably do, let's just solve for y, because we're used to solving for y. So I'll divide both sides by 3. So my y is equal to 3/5 x. So I'm going to change this. I have minus x minus 5/3 of x equals to minus 8. And if you live in my land where you just want to make this all positive, you can just go through and just go, I'm dividing by -1. Boop, boop, boop. Everything's good. Cool. So then I'm going to think of this as 3/3 x, or you can use a calculator to add these two together. But you should come up with 8/3 x is equal to 8. Good times. And then hopefully you remember that I need to get x by itself. So I'm going to multiply both sides by 3/8. 3 and 8 look too similar. That was bad on my part. Yay! So then 3 cancels with 3, 8 cancels with 8. I hate the word cancel because people think that means it's 0. No, you're dividing out and getting 1. 8 will destroy 8 because you're both multiplying divided by 8. That's like doing nothing. I'm going to get 3 for x. Woohoo! And now I need y. Oh, but look, I have a nice way to convert and get y, don't I? Y is 5/3 of x, and x happens to be 3, which is nice because then you get that y is 5. 3 and 5. Good times. That orange is a very pretty color. I like it. I like it a lot. Okay, so we've done a lot of ones where the x and y haven't had a whole lot of meaning. I'm going to take you to one where they actually will have meaning, and you can draw out what your constraints are actually going to be. So suppose, I did it again, where it thinks my pen is my finger and my finger is my pen. Does that every once in a while. All right, so suppose you have a rectangle and it has to have a perimeter of 40 units. I want to figure out what will give me the maximum area of a rectangle. You've hopefully seen these back in algebra times. Now, one of the things you know is that calculus is usually a little faster than algebra. Let's take a look. So I want you to draw yourself a rectangle. I'm going to assume one side is longer than the other, but that might not be the case. We'll call this x, we'll call this y. And hopefully you remember that perimeter is just your length around, so I got to go by x twice, once here and once here, and y twice to make my fencing. So 2 y's, and that has to be 40 units. So there's my constraint. Cool. And then the function I want to maximize is the area, which will be just x times y. Good times. So to make my Lagrangian, I'm going to have x times y minus lambda times my limiting perimeter, 2x plus 2y minus 40. Which I could have probably reduced that, but too late now. Well, evidently my account settings are out of date. No biggie. Let's go ahead and distribute our negative lambda to make our lives easier later. For some reason I didn't do what I usually do, which is put lambda next to the constant. Not really sure why that happened. It is what it is. Let's derive. So let's see, Lx, Ly, L lambda. Ooh, so this is interesting. So for this first term, when I do the x derivative, I'm going to get a y, because I'll derive the x and get a 1. And then a minus 2 lambda, and then nothing else has an x in it. And for the y partial derivative, I'm going to get just an x, and then again a minus 2 lambda. And then for my lambda derivative, I'll get nothing off that first term. I'll get a negative 2x, a negative 2y, and a plus 40. Now we're going to set these all equal to 0. All right. So I'm hoping you see from these two, I'm going to solve for lambda. So I'm going to add lambda to the other side. It's going to have that 2 on that, so I'm going to have to divide by 2. So from the first one, you're going to get that lambda is equal to y over 2. And for the second one, you'll get that lambda is equal to x over 2. So when you combine these two, you'll get that y over 2 is equal to x over 2, or that x is equal to y. This is a proof to you that when I want to maximize area, I want my x, I guess you could call that your width. Is that width? No, height? Yeah, height. And your width have to be the same, or x equals y. Or I need to get a square, which is what I should have probably drawn in the first place, but too late now. Whew. All right, so then I'm going to take this idea, substitute it into here. So I'll have my negative 2x minus 2x now, because y is equal to x, plus 40 is equal to 0. Let's do some algebraing to this. So this is negative 4x. I started to write 2, but negative 2 plus negative 2 is very clearly 4. And then if I subtract the 40 over to the other side, I'll get a negative 40. Let's divide by negative 4. That supplies me with the fact that x is 10 units. I love how vague I was on this. Units. Maybe it was fencing units. I don't know. Oh, and then since x equals y, well then y is also 10 units. And also, another way that I could ask you this question is I could say like, ooh, well, what's the maximum area? Like I did here. Ooh la la. Find the maximum area. It looks like I'm crossing that out. So I've got that x and y are both 10, which means I'm going to take this and put it back into area. So that means my maximum area is going to be 10 times 10, or 100 units squared, or square units, if you will. Let's move on to something that's a little bit more interesting. Now, if I remember, y'all had some issues with cylinders and or shapes that ye have not dealt with in a long time. So I'm going to be very careful with this when it comes to drawing this and what's happening. So hopefully you know what a beverage can looks like vaguely. Like, oh, I have a circle at the bottom, and then, yep, that's as good as it's going to get. And a circle on top. I hate this. So it'll have a certain radius and a certain height, which is kind of fun. And in particular, I have the volume here. I took a can in my house and converted the volumetric units into cubic inches so that we could do this in inches. If you are real bored this week, go find yourself a container that you know how much volume it carries, and then measure it and do this problem so that you can see, is that can or energy drink or water bottle the most efficient it could be for something that size? Well, why do I say most efficient? Well, minimum surface area means that I use the least amount of material in cutting out making the product. So is it as sustainable as it could be? Let's find out. So if I'm doing volume, if you remember the volume of a cylinder, it's like I'm going to take my little tiny circles and stack them up h high. So it's h times the area of a circle, which is pi r squared. And then we also need to do surface area. So imagine taking this can and then cutting a line down the middle here and then rolling out the material that made it. You would end up with a circle for the top, a circle for the bottom, and a rectangle. Yikes. Okay, so radius. These circles should have been the same size, and they're clearly not. And then this is my height. And then you got to ask yourself, how wide is this? Well, it has to wrap around the circle all the way. You know what I mean? Actually, I want to erase that last bit I drew, because that's going to look weird later. So that's equivalent to what we call the circumference of a circle, which hopefully you remember. If not, it's just 2 pi r. Ta-da! So my volume I know to be a specific value, and I've got right here my surface area is going to be 2 circles, so 2 pi r plus that rectangle, which is going to have height, and width 2 pi r. This should be 2 pi r squared. Sorry about that. I just realized I forgot the square because these are circles, you know? Whew. All right, now I've got a lot floating around in this equation. Ay, ay, ay. Oh, and in particular, I know my volume. It's not V, it's 21.66. So I should probably use the number in here since it's a constant. I have a fixed volume I'm looking at, and it's the volume of a soda can I found in my house. Woohoo! I was going to go look for a really weird energy drink that my husband had earlier in the year. Not in the year, oh my god, in the week. Yes, I hold on to cans for a year. That's from Korea, and it had this really pleasing shape, but it didn't seem very efficient. And I was going to do that one, but I wanted to do one that you maybe could go measure yourself once we get the result from this. Now, because there's some rounding here, and I'm clearly using a decimal, there's going to be some parts of this that will be decimal looking. Let's create our Lagrangian. So I've got my thing I'm minimizing, which is surface area, 2 pi r squared. Do I want to fix this up so it has less variables in it? Nah, we'll do that later. Plus, let's do 2 pi RH. I like how that looks better. Minus my limiting equation. So I have to take this and subtract 21.6 over to the other side. So here you would get pi r squared h, oops, I forgot my lambda, minus lambda times 2 pi r squared. That square doesn't want to come out nice. I'm sorry. H minus 21.66. Don't forget that. It's going to be in there. All right, now I need my Lagrange derivatives. So, oh, not x. Be careful here. Your variables are now r, h, and lambda. So I want to be careful. There's no x and y. I'm going to be doing radius and height. Make sure my r looks different than my h. Here we go. So I'm deriving with respect to r. So for this first one, I'm going to get 4 pi r. And then for the second one, I'm going to get 2 pi h, because I derive r and get 1. I'm going to put little loops on the top of my h's, because they're starting to look like r's. I like that better. Fix them all. I wish I'd have done that from the start. Too late now. Good job, teacher. Who left you in charge of anything? No one. Oh, I forgot to distribute my negatives. I'm going to be careful here. This last number has like no r's or h's on it, so it's only going to show up in the lambda derivative, so I can kind of ignore it and just do this one. So I'll get minus, oh boy. So I'm deriving r, so I'll get a 4 pi. I get a lambda. I'll have an r left over from when I did my derivative, and an h. There's a lot going on with that equation. I'm a little worried about that one. Let's do the next one. So for the next one, this first term has no h's in it, so that's going to drop off. The second one has an h in it, and so when I derive the h, I'll get 1, so I'll get 2 pi r. And then same thing is going to happen like before, that 21.66, not going to show up in this one, but I'm going to get something when I derive this one. So I'll get minus lambda 2 pi r and then a square. Now this one's going to be nice when I go to solve it, because there's a couple terms that are going to drop off. We're going to get some things for lambda. Let's do the lambda derivative. Whew, this one's going to be gross. So everything's going to drop off from the beginning because it's got no lambdas on it. Those are both going to be 0 when we go to derive with respect to lambda. We're going to get something from this first term, and we're going to get something from the second term. So don't forget to distribute the negative with this. So I'm deriving lambda, which is just going to be a 1. So I'm going to just throw the negative through this, because it'd be like multiplying by negative 1. So 2 pi r squared h, curly h, minus, not minus, distribute your negative, teacher, plus 21.66. Look at that lovely beast of an equation. This is going to take me a couple minutes to finish. All right. Who's ready to deal with a mess? So I am going to take some of this and do it a little bit separately. So I'm actually going to start with this middle one because it looks the most simple to me, and I think it's going to yield the best results for me. So since it's got a subtraction in here, I'm going to try to solve for lambda, because lambda only shows up once up here, and I'm hoping by solving for lambda I can shove that up there and have something cancel or get destroyed or have some common factors go away, because solving this system looks a little messy right now. So I'm going to have 2 pi r. So since I have 0 on this side, I'm just going to imagine adding that over, equals lambda 2 pi r squared. So I'm just going to divide to solve for lambda. 2 pi r squared, 2 pi r squared. And that's good, because everything is going to cancel except for 1 power of r. So that tells me lambda is just actually 1 over r. That came out way better than I thought it was going to. Just kidding, I already knew it was going to be nice. Sometimes it's better when you're looking at these to start with the shorter equation. I didn't pick this one because it's got that gross 21.66 in it. And it's got 2 variables floating around that I really don't think are going to go anywhere. So now I'm going to take this, and who do I want to substitute into? I'm thinking this one. Give me a second. Yeah. Because that will give me 4 pi h. Yeah, that's going to reduce down a little bit to something we can use. Okay, so what I'm going to do is I'm going to do this in a different color. So now I'm taking the RLR derivative, partial derivative, 4 pi r plus 2 pi h minus 4 pi, that's a pi, ew, my pi's are ugly. Now this would have been lambda, but now we're going to do 1 over r, for lambda, r h equals 0. So what's nice is these two are canceling, and making a 1, so I'll have minus 4 pi h. So that allows me to change this into 4 pi r, and then I have 2 pi h's, and I lose 4 of them, so I really have negative 2 pi h. So what's nice is hopefully you're seeing how this is going to solve. I'm going to add the 2 pi h to the other side. I'm going to write this over because I'm running out of space. So I'll have 4 pi r equal to 2 pi h, and I'll divide by 2 pi, divide by 2 pi, bonk, 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 and I'll get a 2. So that tells me that h is actually twice the radius, and that's something that comes up a lot when it comes to canning things, is you'll end up with your height being twice what your radius should be. So the next time you look at a can, like just look at the top and then like measure how big you think the we'll use the diameter because that's 2 radiuses, and then see how close it is to the actual height. It's kind of interesting. Anyway, so now that I've got h, and I've got a way to get rid of lambda, let's use our lambda equation. So do I have more space in this question? I hope I do. Oh, I've got like none. That's going to be awesome. All right. Let's switch to blue. So now I'm going to use this equation. Negative 2 pi r squared h, but h is 2r, equals, and then I'm going to move the 21.66 to the other side, and then remind yourself that I know how to deal with negatives. Cool. So what's nice about this is when I'm done, I'm going to have nothing but r's. So I'm going to take the 2 and combine it with the 2 to get a 4 pi r cubed is 21.66. So this is pretty easy. If you solve for r, you're going to take 21.66, divide it by 4 pi's, and then take the cube root. When you do that, you will get a number. So this is where you're going to be a little careful because I need to round this. It's not going to come out whole. It's going to be like, it's 1.19 and then a bunch of 8s and 9s. So I'm going to call it 1.20, which is probably not the amount I should round. But now that I have what r is, I can use that to then find h. My h is twice that, so h is going to be 2.40, and then, I can also use r to tell you what lambda is if you want it. It happens to be 1 over 1.2. Come on. There we go. For some reason it didn't want to write that one. And 1 divided by 1.20 happens to be about 0.83-ish. It's like 0.8 and then the 3 repeats forever. Clearly there's some thirds in there. Anyway, so I don't know, if you're real bored this week, which I highly doubt any of you will be, you can sit down and do this with any shape. Fix your volume at some size, and then ask yourself what size container would be the most efficient, aka give me the least amount of material I have to use to make it, and then you can build that shape. You can do this with cubes, you can do it with prisms, you can do it with all kinds of fun shapes. Maybe that's something that interests you. I don't know. Trying to inspire you to try some fun math. Okay, let's take a look at a utility function. If you've never seen a utility function before, they are measures of how two commodities interact with each other with some limitation. So the idea is that I have two commodities, x and y. This should be a y. Too late to fix that now. And when I look at the cost of x, it's 2 per unit, and the cost of y is 1 per unit. We want to look at maximizing my utility function, this guy, when I can spend $80. So my limitation here is by cost. So if you notice that x costs more than y, so my cost function would be 2x plus y is equal to what I can spend, which is $80. So that's going to be my limiter here. That's going to make the limitation upon my Lagrangian. So my Lagrangian equation is going to be x squared y cubed minus lambda times my limiter, which is 2x plus y minus 80. That's an 80. Let's do our derivatives. I'm going to do my x derivative, my y derivative, and then my lambda derivative. I don't like my lambdas. If the lambda is driving you crazy, use just like any different letter in there that you've got. Like use an A if you want. Or, if you're Zane, use a Z. Maybe don't use Z because usually you use that and other things. I don't know. I miss you guys. It's real boring doing this by myself. All right, here we go. Let's derive x, ignoring everything else and treating it as constants. Oops, I didn't multiply this out again. That's going to make this one hard to do, so let's go ahead and write it. 2 lambda x, that's not an x, good job, minus lambda y plus 80 lambda. There we go. That'll be easier. So for this first one, we're going to derive the x, leaving the y alone. Derive the x, and that's the last thing that has an x in it, so we're done with that one. Let's derive the y, so we're going to derive y, leaving x alone, so x squared comes along for the ride. I'm going to get a 3y squared. I almost said cubed, that would have been wrong. That's got no y, so it gives me nothing, minus just a lambda. All right, and then last but not leastly, our lambda derivative, get nothing off that utility function because it's got no lambdas. We get a negative 2x, a negative y, and a plus 80. Setting these all equal to 0 to get ready to solve. As usual, I'm going to solve for lambda. So I'm going to move the 2 lambda over to the other side by adding and then divide by 2. So for this first function, I'm going to end up with that lambda is just, well, when I divide by 2, the 2 will go away. So I'll get an x y cubed. And then with this lambda, I'm going to add it over and I'll just get that it's x squared. Actually, let's do 3. Come on, 3. X squared y squared. And you might think, oh, this looks terrible. What am I going to do? Well, we're going to set them equal to each other and come up with some solutions. So I'm going to say, let's see, how do I want to do this? Oh, I'm just going to have to factor like it's my job. It's factored. Fun time in math. There's a tip for you I think I haven't said. When you are ready to just give up on a problem and you're not sure what to do, try factoring because it totally saves your life. So I'm going to set these two equal to each other. So I've got x y cubed equal to 3 x squared y squared. So I'm just going to move this one over to the other side. I'm going to treat my cube as a leading term. So I've got x y cubed minus 3x squared y squared equal to 0. Now I'm going to factor. So greatest common factor is what I'm going to use. So they all have at least 1 power of x and they have at least 2 powers of y. So I'm going to factor out xy squared. I'm having a real hard time with the 2's. So when you look at this first term, what's going to be left is a y. When you look at the second term, it's a minus 3x equal to 0. Okay. Oh, and that's just going to yield me a bunch of factors. So here we go. Let me roll this up a little bit because I'm running out of space. Is that enough? That should be enough. Okay, back to pen. Close that. So what do we get off of this? We actually get 3 factors. Either x is 0, and that's coming from right here. Either y is equal to 0, and that's coming off the y squared equal to 0. Or we get that y is actually equal to 3x, because if I put in 3x for y, this will be 0. Remember, this is something called the zero factor property. If I have a bunch of things multiplying to make 0, one of them has to be 0. So now that we have that, we can use it to actually do some of our solving back in here. So I'm going to start with x equal to 0, then do the y equals 0 case, and then do the 3x case. So we have to go through and do all 3 of these to figure out what's happening. I have a feeling some of these are going to drop out and turn into nothing, which is not going to be helpful. So let's start with this first one. So I'm going to have x be 0. Let me erase that. That was way too big. It's going to take up too much space. So I'm doing x equals 0. So in looking at the lambda derivative, that's going to give me that my first term is nothing. So negative y plus 80 is 0. So that gives me that y is actually just 80. So there's my solution for that one. Woohoo! And we're going to play the same game with y. We're going to have y be 0. So then I have negative 2x minus nothing plus 80 is 0. So remember, y is nothing in this scenario. So then I have negative 2x. I'll subtract 80. And then divide by negative 2, and that'll just give me 40. Negative 20. What am I doing? So for this one, x is 40. So there's a second solution for us. And then my last scenario is that y is actually equal to 3 times x. So for that one, I'll have negative 2x minus y, which is 3x plus 80, is nothing. So I'm going to subtract the 80 over, combine my x's, that's negative 5x equal to negative 80. We'll divide by negative 5 on both sides, and hopefully you know what 80 divided by 5 is. So 80 divided by 4 is 8, so I think it's 16. Yes. Yep. Why isn't my pen working? Come on. Yeah, there we go. Sorry, having a little bit of a hard time. And this is good because now that I know what x is, we can go back to this and say, hey, x is 16, y is 3 times that, so that's going to give me that y is, that seems, 16 times 3 is giving me a brain fart. Yeah, 48, okay. Second guessing myself, so I'm just pulling up my calculator and making sure. Cool. Now, these are your 3 possibilities. And remember, these are optimizations. So one of these is the maximum. Don't know which one's the maximum. So at this stage, we're going to have to do some checking. So I'm going to go back to the thing I'm actually trying to maximize. Maximize. Ooh, voice. This guy, my commodity. So I'm going to be using f of xy to do this. So hopefully you notice that f of 0, 80 will be 0, because it's just going to be, 0 squared times 80 cubed, which is nothing. And then f of 40, 0. So that was this guy, and then now I'm doing this guy. That's going to have the same problem. I'll have 40 squared times 0 cubed, which is going to be 0. And then hopefully you're like, oh yeah, that's going to be the one that gives me something interesting. So f of 1648, and this I definitely can't do in my head, is going to be 16 squared times 48 cubed, which is going to be like in the range of like 28 million something, $311,552. Gee, I wonder which one is my maximum. This one. So that would be your answer. Good times. Okay, so what do we get from optimization? Sometimes you don't have to do the d-test, and sometimes when you're looking at a system, it will have constraints. Don't forget your 5 steps at any step you are looking at. Make sure that you're practiced with this, because we will have a quiz on it this week. Yeah. And don't forget to rewrite your constraints, because that's a common mistake. That's this step. Making sure that it's with the minuses and stuff. Okay. Some of the problems on your homework, I think there are lots of places to make little mistakes. So if you're struggling and you need some help, don't forget I'm available to you. You should totally let me know if you want to get together and meet for some online office hours. I gave you guys the survey with a big list of possibilities of when we can meet. If you haven't done that survey, please do it like as soon as possible, because I want to pick some times that work for everybody, so that should you need help, I'm available. That's it for today. Hope y'all are living your best life.